last thing we talked about was the law of conservation of energy, right? And what did we say, what happens with the law of conservation of energy? What is conserved?
Energy.
Yeah.
Can't be destroyed or created.
Yeah, energy cannot be created or destroyed. What do we know about matter? Can matter be created and destroyed?
No.
Or destroyed. That's a law of conservation of mass, right? But we know from nuclear reactions what happens to that mass. It goes from having a mass to just being converted to pure energy. So law of conservation of energy is typically only true chemical reactions. But we can break like subatomic particles up, right? Anybody know who Richard Feynman was? Okay. Richard Feynman was a particle physicist, a really brilliant guy. If you ever get the chance, read the book, Surely You're Joking, Mr. Feynman. What he would do is he would work on his physics problems. His favorite place to work on them was actually the strip club. So he would go to the strip club, he would work on things, and he would ogle ladies while he would do this. The other interesting thing about the guy is he took his entire sabbatical and just decided to go play bongos in Africa. Like, just ditch everything, let's go do that. Really interesting dude. If you get a chance to look up some of his interviews on YouTube, they're really awesome. Yeah. But he came up with these really interesting diagrams to explain a real complex idea in particle physics, where things smack into each other, they break apart, and they were called Feynman diagrams. And we're going to draw a couple of these Feynman diagrams. You might be asking, why are we taking this tangent? Well, it has to deal with showing that energy cannot be created or destroyed, but mass can be created and destroyed. It's all energy. We're all energy. We're all just waves oscillating at different frequencies when you really look at it all. It's pretty crazy. So let's talk about these Feynman diagrams. So we have an electron. Does anybody know what is the counter to an electron? Like, what do you call something that has the exact same mass but the opposite charge of an electron? Anybody know? It's called a positron. How many people are psych majors or like behavior and neuroscience? Anybody? Okay, like they do PET scans of people's brains or positron emission. I don't know what the T stands for, but they look at positrons coming out of people's heads. So they're a subatomic particle. They have the exact same mass as an electron, but the opposite charge have to exist. Now, what do you think is going to happen when this negatively charged particle meets this positively charged particle? What are they going to do to each other? See the hands, they got like one look like Pac-Man fighting out over there. Yeah, they're going to connect. What they do is they meet each other because positive and negative, they attract one another, right? And they actually annihilate one another. They disappear. And what they do is they create a photon of energy. So in these diagrams, these symbols, gamma was given for a photon, E plus was an electron, E minus was an electron, E plus was a positron. So this is known as pair annihilation. And what happens, matter that once existed, we could measure these things, we could see them, they meet one another and bam, they make a photon. Now, could the opposite be true? Could a photon just be bopping along and spontaneously create matter? Yeah, it can. So if you have a photon of the correct wavelength, what can happen is it'll just be bopping along, and then it'll spontaneously spit out a positron and an electron. And this is known as pair production. which is a pretty crazy process to think about. So it's like we're making particles that have mass from nothing. Pretty cool. Yeah.
Doesn't matter which particle you're on the bottom.
Oh, no, it doesn't really matter. They're the same. But what Feynman did is there's really advanced mathematics here that take play. And he took those really complex ideas and he made these little diagrams. These little diagrams make way more sense. They're way easier to understand than like the eigenvalue, eigenproblems, trust me. So that's pretty cool. So in this case, law of conservation of energy is followed, but law of conservation of mass isn't, which is a big point.